So today in MT5504, the mathematical programming, we are at the BGAM method at the state 4. We will see today a problem which is not having a feasible solution. So first of all we will see by BGAM method, and then we will see that actually it is having no feasible solution by graphical method. So to get the graphical method we must have a problem with at most two variables. So we are writing problem with two variables. Maximize z is equals to 4x1 plus 2x2 subject to constraints 2x1 plus x2 is less than or equals to 4, 5x1 plus 3x2 is greater than or equals to 15, x1 and x2 are non-negative. So directly I think you can see that whenever this is satisfied, this will not be satisfied, but we see by graphical first of all by BGAM method. So since here constraint is of the greater than or equal to type, we have to add a surplus variable and the artificial variable. I am adding both together. So the standard form of given LPP is, first of all, maximize z is equals to 4x1 plus 2x2 subject to constraint 2x1 plus x2 plus s1 is equals to 4, then 5x1 plus 3x2 minus s2 is equals to 15 with x1, x2, s1 and s2 are non-negative. But here if we go for x1 and x2 is 0, then we are having s1 is equals to 4 and s2 is equals to minus 15. So we are not getting a feasible solution. So instead of going directly, we are adding artificial variable. So after introducing artificial variable, we have here s1 and s2s are not there in the constraints, so 0 s1 plus 0 s2. Okay, but when we will introduce the artificial variable, its coefficient is minus m, since your objective function is maximize z. So here it will be maximize z is equals to 4x1 plus 2x2 plus 0 s1 plus 0 s2 minus BGAM times artificial variable a subject to constraints 2x1 plus x2 plus s1 is equals to 4, and in the second constraint we are adding the artificial variable, so that is 5x1 plus 3x2 minus s2 plus a is equals to 15. Here your x1, x2, s1, s2 and a are non-negative. So this is the standard form, and to get the initial basic feasible solution we are considering x1, x2 and s2 be 0. So your s1 will be 4 from the first constraint and your artificial variable's value is 15 from the second constraint. Okay, so now we have to make the simplex table for this. So the simplex table is as previous cases. Values are, first of all, basis, coefficients from the basis, its value, then variable x1, x2, s1, s2 and your artificial variable, its coefficients from the objective function. Here it is 4, here it is 2, 0, 0, minus m, and in basis right now we are having s1 and a. Coefficient of s1 is 0 and coefficient of a is minus m. Then value of s1 is 4 and value of a is 15. Now write down the coefficient from the objective constraints. So from the first constraint, x1's coefficient is 2, x2's coefficient is 1, x1's coefficient is 1, x2 and a is not there. Then x1 coefficient is from the second constraint 5, x2's coefficient from second constraint is 3, s1 is not there, and s2 is -1, a is 1. Okay, so up to this is okay. Now the cost line ZJ is evaluated like -m times 5, so -5m, -m times 3, so -3m, -m times 0 is 0, -m times -1, so m, and -m times 1 is -m. Now Cj minus Zj, these values are Cj, so Cj minus Zj is 4 minus 5m, so 4 plus 5m, 2 minus -3m, so 2 plus 3m. Here it is 0 minus 0 is 0, 0 minus m is -m, and -m minus -m is 0. M is again too much large number, so 5m is too much large than 3m. So the x1 will enter a basis, and now we have to evaluate the replacement ratio. So replacement ratio is 4 by 2 is 2, and 15 by 5 is 3. So minimum from the replacement ratio is 2, so your S1 will leave a basis. So we have to make this entry 1 and this entry 0. So applying RRE process, first of all I have to write the table. So XB, B, CB, X1, X2, S1, S2, A. Since still A is in basis, so we have to keep there. Okay, and here S1 is replaced by X1, so here in basis you are having X1 and A. Coefficient of X1 is 4, coefficient of A is -m. Now to make this entry 1, we have to divide by 2. So 4 by 2 is 2, 2 by 2 is 1, 1 by 2 is 1 by 2, 1 by 2, 0 and 0. Now to make this entry 0, we have to multiply this row by 5 and subtract from here. So by doing that process, we are having 2 times 5, that is 10. So 15 minus 10 is 5. Then 5 minus 5 is 0. Then 3 minus 5 by 2 is 2.5. So 3 minus 2.5 is half. Then 0 minus 5 by 2, so minus 5 by 2. Minus 1 times minus 0 is -1. And 1 minus 0 is 1. So this is your second table. Again, let me write the coefficients from the original table. So values are here 4, 2, 0, 0 and -m. These are Cj's. Now to evaluate the values of Zj, again multiply 4 times 1, that is 4 minus plus -m times 0, so it is 0, so 4 times half, that is 2, and -m times half, that is minus half times m, so 2 minus m by 2, and here 4 times half, that is 2, minus m minus 5 by 2, so plus 5 by 2m. Here that is 4 times 0, so 0, and -m times -1, so m. Here 0 times 4 is 0, and -m times 1 is -m. So Cj minus Zj's are here 4 minus 4 is 0, 2 minus m by 2, so here it is m by 2. Here 0 minus 2 minus 5 by 2m, so -2 minus 5 by 2m. 0 minus m, so -m, and -m minus -m, so 0. So positive quantity is only for this, x2 will enter a basis. Now find out the replacement ratio. So for 2 by 2 by 2, 1 by 2 is 4, and 5 by 1 by 2 is 10. So minimum from this is 4. So 4 will corresponding variable x1 will leave a basis and x2 will enter a basis. So we have to make this entry 1 and this entry be 0. So to make that, we have to multiply the first row by 2 and subtract from the original row will be subtracted from the second row. So again, let me write the table. So here we are having xb, b, cb. In the basis we are having now x2 and your artificial variable a. Coefficient of x2 in our objective function is 2, and here it is minus m. xb, now this whole row is multiplied by 2, so here value is 4. Let me write x1, x2, s1, s2 and a. Its coefficients are 4, 2, 0, 0, minus m. To divide the first and second table and drawing a line. Now 1 is multiplied by 2, so 1 by 2 is multiplied by 2 is 1, 1 by 2 is multiplied by 2 is 1, then 0, 0. Now subtract from second line the first line, means 5 minus 2, so that is 3, 1 minus 0 is minus 1, 1 by 2 minus 1 by 2 is 0, minus 5 by 2 minus half, that is minus 6 by 2, so minus 3. And minus 1 minus 0 is minus 1, 1 minus 0 is 1. Again evaluate zj. Zj is 2 times 2, that is 4, minus m minus 1, so plus m. 2 minus 2 times 1 is 2, so 2 minus here it is 0. Okay, so 2 then 2 times 1, and that is 2, minus m plus minus 3, so plus 3m. 2 times 0 is 0, minus m times minus 1, so m. 2 times 0 is 0, and minus m times 1 is minus m. So cj minus zj is 4 minus m, so minus m. 2 minus 2 is 0, 0 minus 2 minus 3m, 0 minus m is minus m, and minus m minus minus m is 0. So here all quantities are less than or equals to 0. So the corresponding solution should be your optimal solution. Less than or equals to 0. So corresponding solution should be your optimal solution, but here we are having artificial variable appearing in the table. So this solution is artificial variable, not your original problem solution. So this given linear programming problem has no feasible solution. You can check in another way also. See, take your value x2 is equals to 4. I am calculating that again. Okay, just checking that your x2's value is 4 and all other variables are 0. So x1 is 0. So insert that in your original problem. So x2 is equals to 2. So this and x1 is 0. So this constraint is satisfied. But here x1 is equals to 0 and x2 is equals to 2. So here value is 6. 6 is equals to 15. That is not satisfied. So our last solution is not feasible one. Okay. So this way also you can see that our given linear programming problem is not having a feasible solution. Or let's we are having a two variable situation, so it is also we can check by graphically. So let me write that problem again. Our problem was maximize z is equals to 4x1 plus 2x2 subject to constraints 2x1 plus x2 is less than or equals to 4, 5x1 plus 3x2 was greater than or equals to 15, with x1 and x2 are greater than or equals to 0. So this was our problem. Instead of x1 and x2 if we replace by x and y, then it will be better to see by graphically. So instead of x1 and x2 I am writing everywhere x and y only. So let me write here, it is x, here y, x, y, x and y. So instead of x1 x2 greater than equals to 0, we will have x and y greater than equals to 0. Okay, so now your problem is maximize 4x plus 2y subject to 2x plus y is less than or equals to 4 and 5x plus 3y greater than equals to 50. So let's see that actually this given linear programming problem is not having a feasible solution. So to get that from the first constraint, the line we are having is 2x plus y is equals to 4. So let me draw xy plane. So let try to draw this line. So I am taking 2 centimeter is equals to 1 unit scale. Okay, in both axes. So here it is 1, 2, 3, 4, 5, 6, 7 and so on. Here it is 1, 2, 3, 4, 5, 6 and so on. So let first of all put x is equals to 0. So if x is equals to 0, then your y is 4. So x is equals to 0, y is equals to 4. So this point. Then put y is equals to 0. Then 2x is equals to 4. So x is equals to 2. So this point. So these 2 points are on this line. So line joining them is our required line. So let me draw the line passing through these 2 points. Okay, so this is a line which is passing through these 2 points, means this is our required line, and we are supposed to check that 2x plus y is less than or equals to 4. 0, 0 is satisfied by this. So the region below this line is our required one, and of course we are in the first quadrant because of your x and y are non-negative. So this region is satisfied by the first constraint. Okay, now from the second constraint we are having that 5x plus 3y is equals to 15. So take x is equals to 0, then 3y is equals to 15, so y is equals to 5, and take y is equals to 0, then 5x is equals to 15, so x is equals to 3. So 0, 5 and 3, 0 are 2 points on this line. So let's draw that. So to draw that we use 0, 5. So x is equals to 0, y is equals to 5, so this point, and x is equals to 3, y is equals to 0 means this point. So let's draw the line passing through these 2 points. Is this. Now we want the region which is having 5x plus 3y is greater than or equals to 15. So 0 0 not satisfies this, means a point not containing 0 0 is region which is not containing 0 0 is the required region made up by this line. So above this line, the region, this is our required one. It is again unbounded. Okay, so this direction fully is covered by that condition that 3x plus 5y is, 5x plus 3y is greater than or equal to 15. So the common region to the first condition and second condition is empty, and hence you can say that it is not having a feasible solution. So we have verified by two ways, that one by actually big bang method, which is ending at the last table with artificial variable appearing in the basis, and all Cj minus Zj's are greater than less than or equal to 0, means we are reached to the optimal solution, but it contains artificial variable, means your given linear programming problem has no feasible solution. And by graphically also we have seen that common region satisfying both condition is not there, means again our given linear programming problem has no feasible solution. Okay, so we have seen that in any big M process, if Cj minus Zj are all less than or equal to 0 and artificial variables are appearing in the table, then given linear programming problem has no feasible solution. Okay, so today we have seen one problem which is not actually having a feasible solution. We will see further that given in a big M method, again when big M method or in a simplex method, when we can go for the multiple solutions, as we have seen in a graphical method, that some problems given which are having multiple solutions. So in the next lecture we will go for that type of problem which are having multiple solutions, and identify multiple solutions via big M method or a simplex method. So till that, stay at home and stay safe. Thank you.